our schedule and what to expect. So we're going to have a test over, it's a non-calculator portion test over what we've been covering this past week. So such as power rule, that'll be a carryover from the last quiz. And then average value theorem, second theorem of calculus, U substitution, and there's even and odd functions. And then there's one more thing, one or two more things that I need to go over with you, but we can do that over the course of this week. So yeah, I think I'd like to just spend a couple of days just going over the test review packet that you just picked up. So it starts with 4.3, 4.5 review, but then it switches over to Unit 4 review. But also need to kind of start squeezing in the calculator portion of your test, which will be next Friday. But first, okay, so I'm going to flip-flop and have the chapter test, the non-calculator portion of your test this Friday. And then the calculator portion will be next Friday. And then along the way, we're going to kind of squeeze in a little bit of some calculator portion that's in preparation for next Friday. And then next week, we're going to do more calculator review. It'll just be 3 problems next Friday. It'll just be 3 FRQ problems. So we're just going to kind of practice through those types of problems. But then we also need to start covering the next unit. So as we're going through the next unit, I'm also going to save some time at the end just for us to do more review for this unit's test. So yeah, this unit has 2 tests of 2 test grades, non-calculator portion this Friday and calculator portion next Friday. All right, so page 1 in your 4.3, 4.3, 4.5 review. And this is what you just picked up right now. Okay, so it says given f of x find the average value. So in other words, whatever this graph looks like, okay, it's going to end up looking like a parabola. Okay. It's asking, between 0 and 3, what is the average height if we were to average out all the different heights along this curve? Right, that's what we're looking for. We're looking for the average height amongst all these y values between these 2 endpoints. Okay. So it's just kind of give you a visual connection here. We're looking for the average height of the curve. So we have a formula for that. So average value, that's average value theorem. This is the formula we're going to apply here. Okay. And we need to make sure we memorize this formula as well. But it's basically just rearranging your area formula for a rectangle. This portion represents area. Your b minus a represents your width. So it's area divided by the width gives you height. So we could just, first thing is replace a, b, and f of x with this particular problem that we're working on. My A value is 0. My B value is 3. Okay, so now as a reminder, when we're doing definite integrals, I know these are the first numbers that we see, well, along with the coefficient from left to right, but it's the last thing that we do, right? We talked about how we have to, the 0 and 3 is not meant to be plugged into the integrand. It's meant to be plugged into the antiderivative. We have to go through our calculus process first before the bounds have any role in the problem. So I'm just going to take care of what I see between the integral and dx. So we can go through power rule there. So we've converted lowercase f to uppercase f. That's basically applying first theorem here. And then we can now plug in our upper and lower bounds. Okay, upper bound first. I'm going to do some cleanup here. The 2's can cancel out. This is my uppercase f of b minus big parentheses and then lower bound. But it's nice that the 0 will just go away. So this is 27 over 3, which is 9. 9 minus 9 plus 9 is equal to 9. But what we've done is we've done this portion of the problem. We found the quote unquote area, but then we still need to divide or multiply by 1/3 to get to our average height. So sometimes I see students forget about that coefficient in front. You can distribute it earlier if you wanted to, but typically I just like, I like to just see what's in front of me here, do this process that just feels like something that we've seen from before, and then just make sure that there's additional extra step there with that adjusting to get to the height. So f of c is equal to 1/3 times 9, which is equal to 3. So if we were to average out all the different heights across this curve, the average height is going to be a height of 3. Okay, that's part A of the problem. Part A says find the average value, which we have. So part A, we know f of c is equal to 3. Part B is asking, okay, so we know that the graph is going to have to reach that average value of 3, but where does it approach it? Or where does it hit that y value? So we just basically have to take this, plug it back into the original function, and look for the location of the x. Okay, so part B is saying find the value of c guaranteed by the theorem. Find the c value, which is really the x value location of the average height. Basically asking, we're just looking for the order pair. We know what the y value is. We're just having to find that x value. So back to the original function. We know what y value we're targeting. Just having to solve for x. Okay, so remember, Anytime we're dealing with a quadratic, we got to make sure that the zero's got to show up. We can't just factor and set equal to 3. We got to set equal to 0. So I'm going to subtract 3 from both sides. The 3's cancel out. That's nice. So I don't have to go through trinomial factoring and just do a GCF here. Factor out the x. So x equals 0. And x minus 2 equals 0. So my c value is 0, and c is equal to 2. We need c values that live between the endpoints, but for average value, it's okay for it to land at the endpoint. Okay, so 0 we can keep, and we can keep 2 as well. Okay, number 2, average value as well. But this is with trig, so we need to recap our knowledge of unit circle values. Okay, everybody okay with 1? Find average value. So same formula. Replace all the a and b values with negative power 4 and power 4. Replace f of x with secant squared of x. I'm really not going to do this until the very last step, but I just like to clean this up if I can. So power 4 plus power 4 is going to be 2 power 4, or 1/2. So this is really 1 over 2 power 4, which is really power 2, but if I flip it, it ends up being 2 over pi. Just want to get that cleaned up before I move on to the rest of my problem. You don't have to. You can wait till the end if you wanted to. Okay, so now my attention turns to the indefinite integral. Again, the bounds is the last thing that we do, right? So do we have a rule for secant squared? What's the antiderivative of secant squared? That's what? Tangent, yeah. So remember first semester derivative rules. We know that tangent's derivative is secant squared, so therefore the antiderivative of secant squared will bring us back to tangent. Yeah. So tangent of x, that's the antiderivative. Once we apply antiderivative, the notations go away. Normally we would have a plus c, but we know we can drop the plus c because we have bounds involved. So power over 4, negative power over 4. Upper bound first. Okay, any questions so far? Now, we have to resolve this, right? on the AP exam, if you leave your answer like this is not far enough. And we have to get it down to a numeric value. Now, the previous example, if you plugged in the 3 and 0, this would be sufficient because these are all numeric values. Unsimplified numeric values are okay on the AP exam, but unsimplified trig expression is not okay. We have to get it down. Now, once you get it down to a numeric value and you have a mess of fractions, you can leave those in AP exam. College Board will be okay with that, right? But we got to go further than this. Same as the test as well. If you just leave your answer like this, it's not far enough. We have to use your unit circle knowledge to resolve it. Okay, so tangent of pi over 4 is 1. Tangent of negative pi over 4, again, if you don't recognize a radian measure, you know you can always add 2 pi or subtract 2 pi to get it into a range that feels more familiar, right? So if I do 2 pi, or if I add 2 pi to negative pi over 4, that's the same thing as negative pi over 4 plus a pi over 4, which is 7 pi over 4. So it's the same thing as evaluating tangent of 7 pi over 4. We know that tangent is going to be negative in the fourth quadrant, and we know it's going to be negative 1, right? So 1 minus a negative 1, which is equal to 2. But this is only giving us the area component, right? We don't want to forget about that 2 over pi there. So our f of c, average height, is going to be 2 over pi times 2, which is so the result of my area component is the 2, but it's not the final answer, right? We still have to make sure we don't forget about the fact that we got to take our area divided by the width to get into our height information. Okay. Number 3. So this function looks a little complicated here because it's got a bound involving variables, and we're asking for the derivative of this function. So anytime you see a derivative of an integral involved, we have to think about the second theorem formula that we learned. So I'm going to abbreviate it. Second fundamental theorem of calculus is this process here. Okay, rather than taking the full antiderivative and then turning around and undoing everything, we're just going to skip that process. We know a lot of those things are just going to cancel each other out. So here's the formula. I want to find the derivative of a definite integral with the lower bound being a constant and the upper bound being a variable. A lot of the calculus procedures will take care of itself, but we do need to keep track of things that's going to happen with this upper bound variable. So the shortcut is that the upper bound will get inserted into the variable within the function times, and the upper bound is going to get impacted by the derivative process, so times p prime. Okay. I know this feels potentially complicated, but it's a lot better than having to do a full integral process and full derivative process. when all you need to do is to do two things with the upper bound. Stick the upper bound into the function, and then worry about the upper bound's derivative and multiply them together. It kind of feels a little bit like chain rule, but it's in the context of undoing and doing, or doing antiderivative and undoing it. So if I want to find f prime, I'm essentially asking for the derivative of this expression. Sorry, everything should be t's, not x's. Okay, so we're just going to follow whatever the theorem says. Right. We're asking for the derivative of a definite integral. So then f of p of x just asks us to plug in the upper bound into the variable. So then every t gets replaced with what? What would that look like? Every t gets replaced with, yeah, negative 2x squared. Yeah. So negative 2x squared over 4 minus negative 2x squared cubed. So that's what this is doing. Times, what's the upper bound's derivative? Negative 4x. Now, I want to make sure that we understand that normally we can't do this, right? Normally you can't plug the upper bound directly into the expression, right? We just got through saying that the upper bound and lower bound, these are meant for the antiderivative. But the reason that we can do this here is because we know that we're going back to where we came from, right? We know that we're asking for the antiderivative and undoing it. And so that process is allowing us to plug in, right? Because we're basically doing two operations on the same function. And we're skipping some steps. Right? So this is a shortcut formula for these two opposite procedures. Okay, so we basically have our answer. Let me just do a little bit of cleanup here. Numerator times numerator. And then the denominator here. The cubed gets impacts everything inside. This is negative 8. 2 cubed is negative 8. And then x squared cubed, the exponents are going to multiply with each other. Okay, any questions? All right, number 4. F of x is the integral from negative x to 3 root x and then again we're asking to find the derivative of this function here. So here we're asked to find the derivative of a function that has a definite integral in it. We know that these are two opposing operations. We're looking for a second theorem to help us out here. So if I want to find f prime would be essentially asking for us to do the derivative of this expression. Now, what's different about this function versus the previous one? What big difference do you see? Anything stand out about how these are a little different from each other? Yeah, the bounds. So here, the upper bound is a variable, the lower bound is a constant. We know we can ignore the constant. But here, upper bound and lower bound are both variables. We know that they're both going to have a certain impact on the problem. This time, the lower bound is not going to disappear. So the second theorem is going to be applied with the lower bound as well. So let me write out that variation of second theorem. So the variation is the upper bound will get inserted just like before, times p prime. But this q of x, this lower bound variable, is also going to have a certain impact. So it's going to follow the minus sign here. After the minus sign, we repeat the same process that we did with the upper bound. So it's going to be f of q of x times q prime. So it's a little bit more than this original theorem, because the lower bound with the first theorem is a constant, it'll just wash out. But this variable, if it's a variable, we know there's going to be some left over after the upper bound is done. Okay, so we're just going to follow the formula here. First step, f of p of x. Take the upper bound, insert into the variable of the expression. Just doing a direct substitution. We're not doing any derivative or integral here. Times the upper bound's derivative. So I got to go through power rule here. 3 root x, the same thing as 3x to the 1/2. So we got to go through power rule there. So this is my f of p of x. This is times p prime minus, then repeat the same thing with the lower bound. Insert the lower bound into the expression. That's where that f of q of x is telling us. Times lower bound's derivative. Negative x's derivative is -1. Right, let me just do some cleanup in terms of distributing and resolving these negative exponents. And here, I'm just making the two negatives canceling out each other here. So I'm just left with 1 plus 2x. Distribute the 3 over 2 root x through my parentheses. Okay. Number 5, let's review even and odd functions. Does anybody still need to look at 4? Okay, so we have two properties here that we want to put onto our graph. And we talked about how there's a certain order that I want us to do this in. And the first step is focus on your shorter interval. Right? So build your shorter interval first. Okay, so which one is the shorter interval? From -3 to 6 or from 3 to 0? 3 to 0. Okay, so we're going to focus on this. But there's something that is a little off about this in terms of our graphing. What do you notice is a little off about this definite interval? Yeah, so this is going backwards here. So this -4 is not really showing us what we want to see, because we would prefer the bounds be what? From lower to higher, right? So from 0 to 3. So this -4 is kind of misleading. So if I rewrite this, this is really showing us an area that's where +4, right, above the x-axis. So just be aware that sometimes if the bounds are out of order and you're trying to graph it, the number that you see, it may be opposite of what you really need to graph. So what we really want to be able to know that this is really showing us 4, right? So we're going to start here. Part A is creating an even function. So from 0 to 3, we're going to create a region and call it 4. Above the x-axis. Okay, as soon as we get done with that shorter interval, we still want to do something with it. We still don't want to move to the larger interval. We want to go ahead and fill out the other side. So this is showing 4, and it's an even function. What do I know about the other side? Also what? Even function. This side is 4. This side is the 4, or is it -4? 4, yeah. Even function, you want a mirror image. So now we can fill in the missing gaps. Okay. Understand that whatever you've already created is set in stone. We don't want anything to add to this. Okay. So we want to figure out from -6. We know that from -6 to 3, all these values, I'm sorry, yeah, from -3 to 6, my bad. This is what we're looking for from -6 to 3, but that's not what we're given. The other property that's given to us from -3 to 6. Sorry, this is -3. From -3 to 6, we know that the area is going to total to be 10. We already have 8 showing. What do you know about the missing portion? Must be what? 2. So if this side is 2, then what do you know about the missing side on the other half of the graph? This must also be what? 2 as well. Yeah. Make sure you don't do a whole big overlap, right? You don't want to say, oh, this is 4 and 4, and I'm going to put something over it and call it 2. Then you're adding something above 4, and this region is no longer 4. So just keep in mind that whatever that larger region is, if there's an overlap, that you have portion that's already set in stone, you're just trying to figure out what missing piece so that all those will add up to that larger interval. So now we're trying to figure out the region from -6 to 3. And that gets us what? 10. Okay, let's do an odd function. Same property, same starting points. Okay, we adjusted the bounds from smaller value to larger value, which allowed us to change the sign, which allowed us to see what it really should be. That it's a +4 and not -4 backwards is +4. So it's easier to visualize what the graph is doing here rather than leaving it in this form. All right, but it's an odd function here. So what do I know about the other side? Opposite, right? So it's going to be -4. Okay, now let's move on to our larger region. There's an overlap from -3 all the way to 6. We know that all this is going to total to be 10. So we already have -4 and 4 showing. What must be the region from 3 to 6? 10. All right. We need all these numbers to add up to be 10. -4 plus 4 is going to zero out. We still have 10 unaccounted for, so 10 is going to have to be here. And if this is 10, and it's an odd function, the other side must be what? -10. So now it says find the region from 0 to 6. It's going to add up to be 14. Okay, there's one more slight new topic that I want to go over with you. That's going to be on the test. So if you guys can turn to page 2, I'm going to have you guys cross off number 6 here, and in place of it, I want you to write this problem down here. Sorry, x minus 2. So this is asking for us to evaluate the definite interval involving absolute value functions. So there's 2 ways to do this. Absolute value, you can rewrite it as a piecewise function. You can go through power rule, but it's a little bit cumbersome. I think the easier way to do this is we're going to use geometry. Okay? We know that ultimately we're trying to find the area under a region. Normally, area under a region is difficult to do with geometric shapes because if you have all these curves, the curves don't nicely fit into a geometric area formula that we know. But if you're dealing with absolute value functions, what happen is you're going to get two straight lines that's going to kind of looks like a V, right? And that V can help us because we should be able to see some easily recognizable shapes that's going to come out of it. And the idea is that these are going to come out to be nice triangles. And if I can just add up the two triangles or add up my triangles, then essentially I'm going to get to my area where if I just have curves involving x squared minus 4x plus 3, it's not easy for us to use geometry. But here, rather than going through power rule and messier rules, we're just going to draw the graph, visualize the graph, and add up the two triangles for our area, right? Remember, depth integral is area related. As long as it's above the x-axis, it's virtually identical with area that we associate with. So first is, let's graph what this looks like. Absolute value of x minus 2 is telling us that there's a vertex at 2. Whatever causes my expression to be 0 is the center of your function. So at 2, 0, we can go ahead and highlight that point. This is going to be where your two lines are going to meet. And you're just going to extend your graph in a V shape. Now, we're only looking at a region from -2 to 3. So just going to mark off -2 and highlight that point. You don't have to be accurate here. We can find these values later. And you're going to drop that line down, and you're going to see one triangle form. And the other one is going to be from 2 to 3. It's going to be a smaller triangle because it doesn't go as far. So if I can find the areas of these two regions, I'm essentially going to find my answer here. So I'm going to find the location of this point because the location of this point is also going to represent, the y value will represent the height of my triangle, right? So if I plug -2 into the function here, right, or into this function here, what's -2 minus 2? -4, right? Okay, what's the absolute value of -4? 4. So my order pair here is -2, 4, and that 4 is the height of my triangle here. So the height of my triangle is 4. The width of my triangle here is 4. And I can do 1/2 base times height to get the area of this region. All right, let's find the y value at this point. If I plug 3 into the function, what's 3 minus 2? 1. What's the absolute value of 1? Still 1. Okay, so my order pair is 3, 1. I'm focusing on that 1 there because 1 is the height of my y value. So 1. What's the width of my second triangle? Also what? Also 1. Okay, so what's the formula for area of a triangle? Area of a triangle is what? 1/2 what? Base times height. Yeah, so we got to do that twice, right? So 1/2 base times height, 1/2 4 times 4, and then the other triangle 1/2 base times height. So we have 16 over 2, which is 8, plus 1/2, so 8.5. So if we're seeing absolute value, we're not going to go through power rule. It's just faster to just draw the graph out, and you're going to get nice geometric shapes. So just add up the two triangles for your depth integral. Okay, your homework is to finish the rest of page 2. The key is on the next page. All right, come get your phones. I'll send out a reminder this afternoon.